Mayuri is from Bengaluru. So, and she became associate fellow last year, and she will be giving a talk titled Experimental Cosmology at Radio Frequencies.
I thank the Academy for this opportunity. I took the liberty of making a slight modification in the content I'd put in the abstract, and I'll be presenting half the work in the interest of time. I'll be focusing on this upcoming cosmology experiment that I'm leading with a nice team at Raman Research Institute, and I also want to acknowledge SCRB for some of the funding. So a lot of the results I'm going to show you are from the preparatory work for this upcoming cosmology experiment at radio frequencies. Hopefully I'll start with motivating the problem first. Before that, I want to acknowledge my colleagues and students, as well as a special acknowledgement to the various interns, undergrads who have come through the lab and who have led some of the results I'll be presenting. So a quick overview of the cosmological timeline. The current most accepted model in cosmology is called the lambda CDM model. And while we don't have the beginning of this quite figured out, right? We don't understand the singularity that is T0 and popularly called the Big Bang, and we also don't understand the very first moments after that, which is called inflation, and there are activities and experiments trying to address that. Standard cosmology has a reasonably good understanding of the first few minutes of the beginning of the universe, and we believe that within the first few minutes, all the baryonic matter that you and I are composed of, dark matter and the photons, have already formed. And this is in a very tight interaction. So the universe is a very hot and dense place, and the photons and the baryons are colliding and scattering off of one another, which means that the universe is what we call optically thick. The photons cannot really escape from this interaction. Gradually, the universe expands and cools, and the universe becomes transparent to the photons. But another important aspect happens in this, in these first about 10,000 to 1 million years. For context, our universe is currently about 14 billion years old, right? And which is the formation of the very first atoms, the primordial hydrogen and helium atoms. And another way to look at the universe is starting outside towards in. We are right now in the middle. The universe gradually transitions from being optically thick to optically thin. And at a redshift of about a million, the universe thermalizes, which means what we call as the cosmic microwave background radiation today gets its Planckian spectrum. It actually becomes a black body. So any process for any radiation to be called black body, of course we're all familiar with the Planck spectrum, but a few other important conditions need to be maintained, namely its energy density, number density, and how the photons are distributed, right? The statistical distribution of the photons. So all of these processes are enabled in the very early universe before a redshift of a million by the formation or removal of photons from the bath, as well as by change in the energy of the photon. So any process that kind of distorts or moves or shifts this black body away from being a black body, it quickly recovers. And the processes that are important, are dominant in this early universe, are called double Compton scattering and Bremsstrahlung, which can create and remove photons, as well as Compton scattering, which can move the photon around in energy. So in the very early universe, all three processes are very active. Gradually, as the universe expands and collisions become less effective, these processes phase out one by one by one. And that is the key to the talk I'm going to give today, which is the formation of these very first atoms happens around a redshift of about 8,000 to 1,000, right? Which means that it happens well beyond this redshift of thermalization. So any process of energy injection, any photons that get added to the Planck spectrum will be preserved to date. And it is this that we are trying to detect with this experiment called Apsara. So this is a prediction of the emission of photons from the formation of the first hydrogen and helium atoms that have come from simulations by collaborators, Kluba et al. And it tells you that there are photons that are added to the CMB spectrum all the way today, redshifted today, from very low frequencies of about 100 megahertz, all the way up to a terahertz corresponding to the Lyman alpha peak. And there are also very interesting features that arise from helium and hydrogen interaction and feedback processes. But to give you a context, this signal has never been detected, okay? That is because, Okay, before I get to that. So why is this interesting to us, right? This distortion, what we call the CMB spectrum from recombination, is one of the very few cosmological processes that can be studied today with a very clear time axis. Okay, so it will help us study the thermal and ionization history of the universe with excellent precision, because each of these lines that we are seeing in the distortion has a very clear time stamp. Okay. Secondly, it's a direct measure of pre-stellar helium abundance, and metallicity and abundance is a very actively studied topic in astrophysics, but all our understanding of helium abundance comes from theory, and we are seeing things in the early present universe, but somewhere you could be able to measure the actual amount of helium that got formed in the early universe if you're able to make a precision measurement of the spectrum. It's an additional probe of cosmological parameters. I have two such here: total matter density as well as actual amplitude of the CMB temperature, and each of this has a slight perturbation or results in a slight difference in this recombination spectrum. It's also a very interesting way to study any evidence of other mechanisms of energy injections. Theorists have written papers on using this as a probe to study dark matter annihilation in the early universe. I'm not an expert, but I'm hoping to motivate you with this slide that is a very useful and important experiment in cosmology and in physics. And the reason why the signal has not been detected to date is because this is the dynamic range that we're talking about at the very least. The blue solid line is the CMB blackbody spectrum, peaking at around 2.8 Kelvin. And way down here, about 9 orders of magnitude below, is this recombination ripple or cosmological recombination lines from the very first hydrogen and helium atoms. The best measurement of the CMB spectrum to date is at a part of 1 part per 10,000 or 1 part per 100,000. So we need to get 5 orders of magnitude better than the current best measurement, which I might remind you is over 25 years ago. So technology has improved since then. There are, of course, practical challenges. So the first question we ask is there a fundamental challenge? Is it feasible, even in theory, on paper, to make a detection? And that's what we did way back when. But I won't spend too much time on this. I want to get to newer work, but we can come back to this. So the idea is that we put in simulation various fundamental limitations to a detection of the signal. So we put in a model of the foregrounds that lie between us and the signal, primarily dominated by our own galactic synchrotron emission. The CMB itself, like I said, is 9 orders of magnitude brighter, so we included that. We put in some basic receiver thermal noise, and for different amounts of receiver thermal noise, we can see that there is a nice frequency range for a ground-based experiment. Atmospheric cutoff is at higher frequencies, where the signal to noise ratio peaks, right? So this motivates the use of cryogenically cooled receivers to achieve the required signal to noise ratio in realistic time. So the simulation suggested that for detection, one would need an array of about 100 mini cooled radio telescopes observing the sky for 1 year for a 95% confidence detection. It sounds like a large daunting number, but I'm going to tell you soon that it may be possible. Again, the other thing to point out is the frequency range where it peaks is around few gigahertz. Okay, so we decided to start looking into this frequency range a bit more. An important caveat for all these results is that we assumed an ideal telescope. An ideal telescope has properties like over the entire frequency range, your beam of your antenna, which is the sensing element of a telescope, is perfectly stable across all frequencies. And that brings me to the newer work. So again, one important concept that we kind of brought into the picture was a definition of what we call smoothness. And the reason why this is important, and it sounds like I'm changing tracks here, is because we need to find a way of separating all these foregrounds that I mentioned earlier from the signal to be able to say I have detected the signal. And an important arsenal in our toolkit is that the signal we are trying to detect is very, very well predicted. It has a very distinct shape we are trying to find. So there's a strong pattern. I'll show you that in zoom in soon. But all the foregrounds, astrophysical foregrounds, galactic emission, the CMB, etc., they don't have that shape. So we want to exploit this property as a basis of separation of the signal from the foreground. And that mathematical basis is this function, what we have defined. We call them maximally smooth functions. For the mathematicians in the room, many of you, this is a slightly modified version of a complete monotone function, but we have placed some caveats on how this signal, mathematical shape can change in derivative at lower and higher orders. So without getting into the jargon, this is what the signal looks like in the frequency range of our interest, 2 to 6 gigahertz. So it's a really nice ripple-like feature which cannot be mimicked by astrophysical phenomena, right? But it can be mimicked by our own instrument. So our feasibility study assumed as a basis that we cannot do these things with our instrument. But in practice, an instrument can do this all the time. It can do this by way of standing waves in a cable. It can also do this because when you look at a foreground, which basically is our galaxy, and the antenna beam you're pointing changes in direction at each frequency, it can leak spatial structure on the sky into spectral structure in your data. So basically an antenna can do this. So we have gone on now, yes. So this is an intern, Dashin, who worked with me a couple of summers ago and we are writing this up. So what Dashin did was he took a toy model of an antenna, a sine square theta beam, and let the beam vary with frequency. So what you see below, and I'm sorry, I don't think it's in time sync, the beam is getting fatter with frequency in one case, the beam is shifting in frequency in the other case. And using this as the beam instead, not an ideal beam that was used in the feasibility study, we still find that we are able to recover metrics of signal detection even with a non-ideal antenna. And we're using very simple things like Pearson correlation coefficient or some Euclidean distance to distinguish between the case where a signal is injected in our model as well as in a null hypothesis case, signal is absent. And we're able to tell the difference, okay? So that leads us to building the actual thing. So we have some parameters that we think are more sacred in the antenna design versus other. So keeping those in mind, we have already built this antenna which has been tested in the field and validated to be ideal to 1 part in 10,000. Okay, and we're also putting together the first cryogenically cooled receiver chain that will go with this antenna, and we'll be out in the field, I guess, by the end of the year. And just with this one element of a nice antenna with a cooled receiver, we can do some very interesting science. First of all, if you look at the frequency versus CMB measurement plot to date, all the beautiful numbers I told you, 1 part per 100,000, is at very, very high frequencies. Okay, about at least 10, if not 20, 30 gigahertz. At the lower frequencies where this experiment will operate, the error bars on the CMB are really large. And people have gone to the field and there have been various reports of detection of some excess radio background, and this has been attributed to, again, some exotic dark matter. So this is open play area for physics and astrophysics, and which is very nice. So we hope to go and tighten the error bars here and see what interesting science lies here, which has not been measured to this accuracy to date. And that can be done with this antenna and this receiver. So the other important thing for this experiment is to go and find a nice site for the experiment. So we were out in various locations in Ladakh last summer to make some of these measurements. And we did a quick RFI survey. This is probably the cleanest you will see anywhere in the world, okay? On the y-axis is just time, x-axis frequency from 500 megahertz to 6.5 gigahertz. And the dynamic range here, we're at minus 90 dBm, which is very, 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 very clean, okay? You don't see any lines at all, and whatever little bit you may see are satellites that you'll never get rid of from anywhere in the world you go to. So we have an excellent site to put this telescope. For contrast, Bangalore looks something like this. The numbers got cut off. I can assure you it's several orders of magnitude worse, which means that we have to stay clear from places like Bangalore or city which have heavy levels of radio frequency interference. The other important reason to go to Ladakh is the contribution from our own atmosphere. As you try to go to higher frequencies and try to make experiments that you want to be sensitive to 1 part per 100,000 and better, your own atmosphere, Earth's atmosphere, can contribute to noise as well as can start attenuating the signal in ways you don't understand. So Tanmay Singh, who was a student with me back then and is a grad student at ASU now, led this work. And what I want you to take away from this plot is that here is Hanle in this little blue circle here. We also found a few other sites. is that the actual thing that is represented in the bubbles here is the number of months out of 168 months where these regions have a precipitable water vapor of 1 millimeter or below. And this is a metric that is very commonly understood in the field of submillimeter astronomy. And this is a bonus thing for us because there is currently a lot of interest in India for astronomers to build a submillimeter telescope in the Ladakh region. So we have done this with what is called reanalysis data that the meteorologists in the room will be familiar with. And we have found that not only is Hanle an okay site, that there may be better sites also out there that are worth exploring for the science, right? And from this, we have been able to make some nice plots like this, which tells you the transmittance of the atmosphere over a wide frequency range. Well, kind of 0 gigahertz, but let's say very, very low frequency, all the way up to a terahertz. And this data, like I said, can be used to not only find an ideal site for this Apsara experiment, but also for a future Indian submillimeter telescope. And this is something that we are writing up and will be submitted shortly. So I may be the first speaker to finish before time, so I may take more questions, but I'll just leave the slides summary up here. I introduce you to what the cosmological problem is and hopefully motivated that it's an interesting problem. Also discussed the feasibility of detection with a very ideal telescope, and also shown you that even with some non-idealities, we are beginning to see that it may be possible. And with the very first element of this array that we are putting together, we can do interesting science with that. We've conducted RFI surveys, and we've also started studying the atmosphere contribution to the noise of this experiment, but also as a site survey for a submillimeter telescope. I'll take questions. Thank you.
Thank you, ma'am, for even before time. Okay. Warning sign.
Yeah.
So we have lots of time for questions.
I have one observation
Yeah.
to suggest you. Can you show India's different cartoon map?
Yes.
Actually depicting the any part of India
Yeah.
correctly is a punishable.
I understand. Yes, yes.
So please do not show this with this blue line as a continuous line. You can just remove that.
We'll do that, yeah. So the red line, of course, we have taken from the India GIS.
This is a public platform.
Yes.
This academy is funded by the Ministry of Science and Technology.
Absolutely, yes.
Officially, the Parliament has passed a Geospatial Act 2016 to show any part of our nation.
Yes.
Differently than it is.
Oh, I understand, yeah. So red line is the line we are acknowledging. I want to put that on record, yeah. Yes.
I am from mid community basically.
Yeah, okay.
Yeah. So this era 5 data.
Yes, yes.
So how good is the data in this mountainous region? Have you done any verification with the in situ observation?
Yes. So
my suggestion is that
yeah.
there are some reanalysis even generated in India. Okay, I can offline tell you that.
Sure.
So IMDA reanalysis, we have some GFS reanalysis where more of Indian data has gone.
Right.
Era 5 uses less Indian data due to various reasons. Can also try to look into that.
Absolutely.
There are some very good satellite data also coming.
Yeah.
Where I think this water maybe, but I have some reservation of Era 5.
I understand, yeah.
How good it is over Ladakh.
Yeah. Yes.
Because reanalysis, basically, I mean, it is very common. Reanalysis means the observation that I am not getting today, I am getting tomorrow.
Yes.
I am reanalyzing the data and preparing a more accurate representation of the atmospheric state, right? But for Ladakh, there is neither any data today, nor there is any data tomorrow, nor there is any data day after tomorrow. So, it will remain same as it is.
Yeah.
Okay. It not affect your accuracy.
No, I understand, I agree. So what we have done is, we're doing two things to address this, and I'll be happy to take the Indian analysis from you. We also wanted to compare this with other global sites, so we used ERA 5 because it's global. We used ERA 5 analysis against one set of measurements we found at Hanle at the Indian Astronomical Observatory, and on that basis we choose ERA 5 over MERA 2. So that is the best we could do. We are in the process of putting together some mini portable PWV measurement systems using GNSS, and hopefully we are going out this summer to deploy the first of them as a trial, and we plan to deploy this all over because we want on-ground measurements at some of these locations that I showed, but it will be great to get higher quality data for Ladakh for this. Thank you. Yeah.
So I am completely from different community. So in the gas phase chemical reaction, helium plus H2 plus or helium plus H2. So molecular beam experiments, and that give very accurate cross section as a function of collisional energy.
Yeah.
And those are actually verifiable with very accurate theory also. So it gives cross section or rate constant as a function of collisional energy within the range of 0.1 electron volt, where your 0.004 electron volt is 1 terahertz. So those data are published in various internationally reputed journals. So these can be taken and converted to your finding and can be compared because these are atmospheric reaction, higher atmospheric reaction. Those are actually mimicked in the laboratory. Okay, particularly in the West, the experiment in India, people do very accurate scattering theory.
Yeah.
So this is comparable. Actually, one can compare.
Okay.
It's comment.
Okay, thank you. Yeah. So I believe at least this simulation I have on here, this was of course back in 2017 or 2018. And at that time, this was the latest prediction that included also several levels and suborbitals of heliums. In this community, that was the first time this was done. I'll go back to the theorists and see if they are including the more recent measurements and so on for helium.